So now we want to start talking about optimization in multiple variables. So this will be very similar to the optimization that we looked at in single variable calculus, where we're essentially looking for critical points, and so that involves finding where the derivative is zero or where the derivative does not exist, and checking for local max or mins there. Then maybe checking boundary points to see if there's an absolute max or min anywhere. So things like that. Now this is probably, I would say this is probably the most important topic of this course coming out of it, going into statistical theory, and also the probability theory to a lesser extent, but mostly the statistical theory classes, because one of the most important parts of statistical theory is the idea of maximum likelihood estimation. And we saw some little examples of that in Math Tools 2, in some of the homeworks practice problems, where we found the maximum likelihood estimator of, I believe, a binomial distribution, for example. So that idea is extremely important in statistical theory, because it's used in things like hypothesis testing when you're looking at likelihood ratio tests. And then the optimization is also used in other things, not just in the maximum likelihood estimation. But, I mean, you're pretty much doing that in most of the major topics in statistical theory. So this is one of the most important topics. So therefore, we do want to spend a lot of time on it. I have 4 entire days planned on just this topic as of right now. So we're going to go through tons of examples, looking at all of the different cases that can arise. But first, of course, we'll set up kind of the ground rules of how do we find critical points with multivariable functions? How do we tell if there's actually a local max or min there? Because if we remember, not every critical point had a local max or min. So things like that. So just as a reminder of, this idea from single variable calculus, right? So if we have something like f of x equals x squared, and we wanted to find if there were any local maxes or mins or absolute maxes or mins, then what we would do is we would find the derivative, which is 2x, and then we would set it equal to 0. So here this would imply that x is equal to 0. And then we would also find any points where the derivative is not defined, which in this case there aren't any. And then we would check if we had a local max or min there. We could use the first derivative test, or we could use the second derivative test. So things like that. So we'll have some kind of analogous test in multivariable functions. So an example where the derivative did not exist would be something like the absolute value of x. So if you remember, if we define this as a piecewise function, we would have this, right? So namely at the point where this transitions at that corner, so on the graph it looks like a corner, right? Right there is where the derivative does not exist. So this is how we would define the derivative. So it's either 1 if x is greater than 0, and -1 if x is less than 0. So you can see right here that at x equals 0, we don't have any point to find. That's because the derivative does not exist there. But that still makes it a critical point. And we do have a local max there, or an absolute max there. I mean, min there, local min or absolute min, right? So we want to kind of do the same thing now with multivariable functions. And again, we're going to focus on functions of 2 variables, but the same ideas will apply to 3 variables, 4 variables, etc. But you can already kind of imagine why this would be more complicated, right? Namely, we're not going to really have, I don't want to say we don't have graphs to fall back on, but they're a lot harder to come by, right? We need to use some kind of graphing tool or something to really see these accurately, right? But then we also don't just have a regular derivative, right? There's no single derivative we can set equal to 0. Because now if we have a function of two variables, say, right? So if we let z equal f of x, y, then we have two derivatives, right? We have a partial derivative for each function. So we're still going to have the same general idea, though, of setting the derivatives equal to 0, but we're going to have to take both of the derivatives into account, okay? So let f of z equal f of x, y be a function of two variables that is defined on an open set containing the point x sub 0, y sub 0. Okay, so this is a particular point here. So this point, so the point x sub 0, y sub 0 is called a critical point. Critical point if one of the two conditions hold. Okay, and these are going to be, you can kind of extract these from the single variable case, namely that the partial derivative at that point with respect to x and the partial derivative at that point with respect to y are equal to 0. So both partial derivatives are equal to 0, or either partial derivative. So either f sub x of x sub 0, y sub 0, or f sub y, x sub 0, y sub 0 does not exist. Okay, so they either both need to be 0 or just one of them has to not exist. Okay, so very important here that we remember that the first one is an and, the second one is an or, right? So let's just jump into some examples. So first, we're just finding critical points. So we're not relating this to local maxes or mins yet. We'll do that separately. So first, right now, we just want to identify critical points. So remember, critical points need to be in the domain of the function. So I made the mistake in Math Tools 2 at one point and corrected it, right? So something like 1 over x, f of x equals 1 over x equals 0 is not a critical point because it's not in the domain to begin with, right? So just something to keep in mind here. So let's do a couple of examples here. So first one we'll do is, let's say f of x y is equal to, x squared plus 2xy minus 4y squared plus 4x minus 6y plus 4. Okay. So the first couple of things we'll need to do is take the partial derivative with respect to x and take the partial derivative with respect to y. Okay. So first we'll take the partial derivative with respect to x. So we get 2x plus 2y, 0 plus 4, 0, 0. Okay. And we want to set that equal to 0. Now, in most cases, you're going to have x and y, so you're not going to get one solution here. So you're going to need to take into account the other equation you get from the partial derivative of y. Okay. So let's just go ahead and find that first, and then we'll work on solving this system of equations. So the partial with respect to y here would be 2x minus 8y minus 6, and that's it. Okay, and that's equal to 0. So when we have two variables and only one equation, we can't solve it. But with two variables and two equations, now we can solve it. Okay, and there's a few different ways you can go about this. You can look into techniques for solving systems of equations. That might be helpful at this point because naturally that's going to come up a lot. So I'll just do this on the side down here, I guess. The way that we typically approach these problems is by what we call a substitution, right? Where we solve one equation for one of the variables and then plug it into the other equation. And that's the most natural, most like logical way to do it. But you can also combine the equations. So this is very common when you start like working with matrices and doing matrix operations. So you kind of like thinking of this in terms of a matrix, it would be like doing row operations. It's very common there. But the same idea can apply without using matrices. So like we could subtract both equations, for example, or we could add both equations, or we could multiply one of them by something and then add it to the other, right? So we can do all these different arithmetic operations to the equations, which might speed up the process of solving them. The reason why we might want to subtract this one is because then the 2x terms will cancel out and we'll be left with 10y plus 10 equals 0 here. So we're going to end up with y equals -1. Okay. Now, if you do it with the substitution method, if you're more comfortable with that, then you should end up with the same thing. Okay. Now that we know y is equal to -1, then we can take that and plug it into one of the other equations. So 2 times -1 plus 2y plus 4 equals 0. So that's -2. So 2y plus 2 equals 0. Or I'm sorry, I put that in for the wrong variable there. Okay, so that should have been 2x. 2 times -1 here. So still same thing though, right? So then x is equal to -1. So we have a critical point at -1, -1. Okay. So this is the point where if x is -1 and y is -1, that's going to make both of these partial derivatives equal to 0. Okay. So again, the techniques that you would use to solve things like this is broadly known as solving systems of equations. So if you look that up, there's basically the two different main types are, without using matrices anyway, is substitution or elimination. So this, what we did right here is called elimination. But you could just, like, for example, you could solve this equation for x, and then you could, whatever you get, you could plug it in for x into this equation, and then that would be substitution. So it just depends on how the equations are set up. This one, I see that they have the same 2x terms, so it's set up nicely for elimination. Some systems are better set up for substitution. But ultimately, it doesn't matter which one we do. So we do have this critical point at -1, -1. So let's look at this graphically so we can see what the critical point looks like in 3 dimensions. So here I've graphed the equation that we're looking at. So it looks like there's like big holes in it. That's just because it's dipping down further than the where the axes are going to, right? Like it's only capping out at 8. And it looks like actually only like -4 down there. So it's just going too far down or maybe too far up. No need to worry about the holes that it looks like are there. But -1, -1 is pretty visible on the graph. So that's going to be, you can see this would be -1 and this would be -1 on the x and the y. So that's going to be this point right here, this dip in the graph that we see. So now the next question that we'll get into, right now we're just identifying critical points, but the next question we'll get into is, okay, is it a max or a min? And what you might see here is that it really doesn't look like it is. Even though it does have that dip in it, it's not really looking like it's the lowest point. anywhere, right? Because like on the sides, all these points are lower than it, right? So it's not, you know, there's really no like neighborhood that you could take of this, like little circle you could take of this where it would be the lowest point in there. Because again, it's dipping down on the sides here, right around it. And it's going up on the sides over there. So it's definitely not going to be a local max either. So this is likely what we call a saddle point. We'll do the math to know for sure. But that would be something like, if you remember the x cubed graph, at x equals 0, there's a critical point, but it's neither a local max nor a local min. So same kind of idea in multivariable functions. We call them saddle points. So we'll do a separate video on those. But that's what we would expect here. So let's go and look at another example here. So we'll look at one that's a bit more complicated here. So let's say we have the function g of xy is equal to the square root of 4y squared minus 9x squared plus 24y plus 36x plus 36. Okay. So again, we want to take the partial derivatives. Okay. So the partial derivative here, if you remember from the square root function, it's basically going to be the derivative of the inside divided by 2 over that square root of that entire thing. Okay. So we're remembering that this is all raised to the 1/2 power, and then we're implementing the chain rule here. Okay. So with this denominator now, that's going to mean we're going to have to look for points where the derivative does not exist. So the derivative of the inside now using the chain rule, we have negative 18x plus 36, and it looks like that's it. Okay, and we'll set that equal to 0. So that one we'll actually just be able to solve. So this is just, we're looking at where the numerator is 0. So this one, you know, we'll definitely be able to solve very easily. But let's go ahead and take this other one first. So the denominator here is going to be exactly the same, because that was just universal just due to the chain rule. Okay. What's going to be different is taking the derivative with respect to y on the inside here. So we have 8y plus 24, and it looks like that's it. And we could cancel 2's out of all of these, but it doesn't really matter. It's not going to change too much here. So we're looking at negative 18x plus 36 equals 0, and 8y plus 24 equals 0. So here we don't even really need to treat this like a system. We just have two different variables here. So this is going to be x equals 2, right? And this is going to be y equals negative 3. So that means that 2, negative 3 is a critical point. Okay. Because this is going to be the point where both the x and y partial derivatives are 0. But now we also need to look at where is the denominator 0, because that's going to mean that the derivative is not going to exist at that point, right? Actually, it's even more than that, because we also have the square root, right? So anything that's going to make this less than 0 is going to be an issue there. So we're looking for 4y squared minus 9x squared plus 24y plus 36x plus 36 is less than 0. Okay. So definitely not an easy thing to really deal with. And actually this should be less than or equal to 0, right? Because anything that's less than 0 would cause an issue here, because then we'd have a negative square root. But anything equal to 0 would cause an issue because it would be in the denominator. Now, one thing to note is that, again, critical points are only points that are in the domain. If we go back to the original function, the domain of this original function is when this whole thing on the inside here is greater than 0, right? Greater than or equal to 0. Because again, we can't have the negative square root. So because of that, we're really only looking for the places where this is equal to 0, right? So this being less than or equal to 0 causes a problem in the derivatives. The domain is that part greater than or equal to 0, so the part where they overlap is where it's equal to 0. Okay. So we've eliminated a lot of points here by just having to consider where it's equal to 0, but it's still not an easy task. Okay. So these are all the points on what we call the boundary, right? If you remember when I was talking about the domain, the boundary points is kind of like the equivalent of the endpoints on an interval. So this is the boundary of the domain because the boundary would be where everything is equal to 0. And there's not going to be an answer for this. Like there's not just like one XY point we can get for this because again, we have two variables and only one equation to deal with. So we really would just leave it like this. And we would say any point that satisfies this would be a critical point. So this is every point on the boundary of the domain is a critical point. Okay. So we would say boundary point is a critical point. Okay. And if you remember about boundary points with intervals, boundary points can't really be a local max or min. They could be absolute maxes or mins, and we need to check the boundary points regardless when we're checking for absolute maxes or mins. So this really doesn't add any points onto what we would already need to check. So, you know, even though it looks like it's making it pretty complicated, just because it's a complicated equation, it's really not adding any work onto it. But, you know, this will make more sense, hopefully, in context when we're actually looking for maxes and mins. Right now, again, just identifying the critical points.